Let's solve some quadratic equations using the quadratic formula. The quadratic formula located in this box reads as follows. X will equal the fraction negative b plus or minus the square root of the quantity b squared minus 4ac, and that will all be divided by the quantity 2a for any quadratic expression whose value happens to equal 0. And my first example over here, that's in fact exactly what I have. I have x squared minus 6x minus 7 equal to 0. And therefore it will require no prep work, and we can move right on to figuring out what our a, b, and c are. And first off, let's look at the fact that I do not have a number in front of x squared, and so that would imply that a would equal 1. Do not forget that you're supposed to be adding bx, but I am here subtracting 6x. I can rewrite that as adding a negative 6x, and therefore b will be negative 6. Using that same logic, I can say that c is equal to negative 7. So let's go ahead and plug it into the formula. Some common mistakes are as follows. Although you started with a negative 6, make sure you take the opposite of that negative 6 at the front of the fraction. Then over here, when you plug it into the square root, don't forget to use parentheses around the negative 6 on your calculator so that you get a positive 36. And then here's where the a will go and the c, and down here is the a. And so what I'll do is simplify the numerator. And I'm going to specifically now look at what I see here in red. And inside that radical, known as the radicand, it also goes by a very specific name in quadratic formulas. It's called the discriminant. And that discriminant equals b squared minus 4ac. The discriminant tells us the nature of the roots. In this case, if the discriminant is a positive value, I will have two real roots. And we'll define real to be a little bit more specific later on. If I happen to have a discriminant who equals 0, I will only have one unique real root. And if I have a negative value for the discriminant, I will have 0 real roots, but that would mean it would be two complex roots involving imaginary numbers. So, in this particular example, my discriminant happens to be positive 64. Do not take the square root of a discriminant because that's not a discriminant. We're looking only at the 64. Since it happens to be positive, I know I'm going to have two real roots. But I want you to be a little bit more specific in nature. And so I'm going to ask you to not just tell me it's real roots, but in this case, rational roots. And the reason it is rational is that square root of 64 can be simplified to 8. So before we go any further, let's make sure we don't make a common mistake. The discriminant is the number inside the radical, known as the radicand, 64. When I am looking at the nature of the roots, I will need to take the square root of 64 in this particular problem and determine, do I get something that can be rewritten as a fraction or a repeating decimal? That would mean it's rational. 8 can be rewritten as 8 over 1, or 8.0000. There's the repeating decimal. This makes it rational. If I would have had a square root of 65 or a square root of 63, I would not be able to write that as a fraction. I would not be able to write that as a repeating decimal, and we would then say it's irrational. Now, if you look over here to the graph on the right, which I want to make sure that you can still see the connection between the quadratic formula and and solving by graphing, you will see that I have two real roots. And it looks like it might be exactly on negative 1 and 7, and so those would be rational roots. Let's see if that's where we lead to. So I have 6 plus or minus 8 all over 2. If I divide every piece by 2, and you got to remember, every piece must be divided by 2, then I will get 3 plus or minus 4. And then I can go 3 plus 4 and get the 7 that I kind of expected. And I can go 3 minus 4 and get the negative 1, which the graph kind of led me to expect as well. Let's look at the next example, 2x squared plus 8x plus 3 equal to 7. But we'll begin by looking at the graphical representation in which the parabola of 2x squared plus 8x plus 3 is being intersected by the horizontal line of y equals 7. You can see that I should have two real roots, but that's not how the quadratic formula works. The quadratic formula works with the quadratic expression equals 0. So what I'm going to need to do is I'm going to need to subtract 7 from both sides. And as I subtract 7 from both sides, you will notice that this graph has now been vertically translated down 7 units. So the roots that are here were actually the same roots that were here and here when the graph was equal to 7. And there you go. There's the roots. So let's solve the quadratic equation 2x squared plus 8x minus 4, now using the quadratic formula. And we'll establish that a is 2, b is 8, and c is negative 4. And we will appropriately plug it into the formula. Again, it's negative b plus or minus the square root of b squared minus 4ac all over 2a. And we will now simplify the numerator. We're coming up with negative 8 plus or minus the square root of 96. Since my discriminant is a positive 96, I will have 2 real roots, as confirmed by the graph here and here. Now, simplifying radical 96, I will come up with 4 radical 6. Having a radical still part of the fraction means that these roots are going to also be irrational. Now, I should try to at least simplify this fraction, and I can as long as this constant, and this coefficient outside the radical, be careful here, does not have to include this piece, but outside the radical, can all have something removed or factored out. In this case, 4 is divisible here, and here, and here. So I will divide everything by 4 and come up with negative 2 plus or minus radical 6. Now, this is the exact answer. But if I was to go back and confirm this on the calculator, it would be helpful to have my decimal approximations. And so I will find out that this value ends up being negative 4.4495, or in this case, negative 2 minus radical 6. And over here, this value happens to be 0.4495, which is the same as negative 2 plus radical 6. So our last example in this video in which our quadratic equations produced 2 real roots. Let's analyze x squared plus 7x minus 1 equal to negative 3. The quadratic expression does not equal 0, so we'll need to add 3 to both sides, and now use the values of a equals 1, b equals 7, and c equals 2 into our quadratic formula, and that work is shown below. As we simplify the numerator into negative 7 plus or minus radical 41 all over 2, remember that our discriminant is a positive 41, and therefore will produce 2 real roots. But the square root of 41 cannot be simplified into a fractional or a repeating decimal form, and therefore will tell us they are irrational roots. And in fact, square root of 41 can't be simplified at all. And so we might just simply leave our answer, if we wanted it exact, as negative 7 plus or minus square root of 41 all over 2. Now, if you recall completing the square process, you could potentially break it up as 2 separate fractions, negative 7 halves plus or minus radical 41 over 2, and that's fine too. And when we approximate those answers, we will come up with negative 6.7016 and negative 0.2984, which correspond to those points here on the graph.